Okay, so good morning everybody. Today we'll start our class. So all of us know that we are doing E524, which is random process and estimation theory. Today we shall start a new chapter. This is random process. So before defining random process, let us try to conceptualize. So one thing will come to our mind, then what is not random process or what is deterministic process. So let's try to understand what is deterministic process. In our second year BTech class, all of us, we have seen in our second year BTech class that signals and systems, all of us read the signals and systems. And there we see the signals are the quantity or physical parameter which is varying with time. So what is signal? Signal is the physical parameter or quantity which is varying with time. Let's say we have a time t and we have some amplitude, say x, and then say it is varying with time. Or we have some t and we have xt, it is varying with time. So all of the cases, the signal is one thing you have to know, the signal is deterministic. What does it mean? The signal is deterministic. It means that at a particular time t, or say t1, at a particular time t1, xt1 is fixed. So it is not random. xt1 is fixed. For example, what the example we can give? For example, let's see. So whatever be the time, if time is fixed, xt1 is fixed. So it is a deterministic signal. So what? Let's give some example. Let's see. Xt will be equals to, say, a sine omega t. Say a we can take as, say, 5 sine omega t. Okay, so 5 sine omega t, so it is a sine wave. So let's say for t equals to 0, xt will be equals to 0. For omega t equals to pi by 2, xt will be equals to 5, and so on. So that means if t is fixed, xt is fixed. We can give another example. Xt will be equals to, say, a when t is greater than equals to 0, 0 when t is less than 0. This is what? Step function. This is step function. All of us we know step function. So if we draw step function, how it look like? Less than 0 it is 0, and if it is greater than 0, it is a. So it is deterministic. Whatever be the time, it is always be same. So with time, if we measure the signal, the amplitude of the signal will be same if the time is fixed. It will not change. It's not random. So it is a deterministic signal. So the signal is predictable if the time is known. If the time is known, we know what the signal will be. This is the beauty of the deterministic signal, and this is the reason that deterministic signal processing is quite easy, because we know the signal, what it is coming, and it is not changing with time. It is changing with time, sorry. I should not say it is not changing with time. It is changing with time, but at some particular time, the value is fixed. Now let us do one experiment. So So this is a deterministic signal. Now, which one is a random signal? So let's do some experiment. So there exists some signal may exist. So random signal, let's say. Some signal may exist whose amplitude is different for different trial at t equals to say t1. What does it mean? That means it is not fixed. Okay, so if we fix the t and I ask to you what will be the signal, you cannot say, because suppose let us consider a noise coming out from the radio. So if we fix a time, we keep on measuring the amplitude. At some time, say at 1 second, it will be something. Again, we do the experiment, it will be some other thing. So let us take one example. So I'm trying to define how it can. Now let us take another example. Let us take an example. Let's say our signal is xt will be equals to a sine omega t, but a is not fixed. The thing is that here a is not fixed. What does it mean? It means it depends on experimental it depends on experimental outcome it depends on experimental outcome of experimental outcome of or it depends on the outcome of an experiment. What does it mean? Let's say we roll a dice. So roll a dice. So if we roll a dice, 1 may come, 2 may appear, 3 may appear, 4 may appear, 5 may appear, and 6 may appear. So suppose I roll a dice and then something may appear, and the output of this signal or amplitude A depends on what it appears. Okay, so let's write it more carefully. Let's say I have a dice and I roll it. So let's say I have a dice, I roll it, and then what it may come? 0. Okay, let's draw in a fresh page. Suppose I have a dice, I roll it, excuse me. Suppose I have a dice and I roll it, and what may be the outcome? Outcome may be 1, outcome may be 2, outcome may be 3, outcome may be 4, outcome may be 5, and outcome may be 6. And let's say there is a monkey who is and this output signal xt depends on the outcome of the rolling of a dice. Let's say outcome of A or coming single, it depends on, and the output will be 10 sine omega t. So with the single, if it comes, we associate a variable 10. Let's say if 2 comes, then we say 20 sine omega t. So with the 2 outcome of 2, we associate 20. If 3 comes, we associate 30 sine omega t. So outcome of 3, we associate 30. If 4 comes, we associate 40 sine omega t. So outcome of 4, we associate 40. And then if 5 comes, 50 sine omega t. So we associate the 5 as the 50. And if 6 comes, let's say 60 sine omega t. Okay, we associate 6 with the 60. Now let's say there is a monkey, so we have all probe in it. So we have all probe in it. We have all probe in it. And let's say there is a monkey who is sitting around here, and his job is to change the switch. Okay, switch may be here, switch may be here, switch may be here, like this, and it can go like this. And there is a monkey who is sitting here, and so let's say then what will be the outcome xt. This is the signal. What will be the outcome? So outcome xt depends on what is the outcome of an experiment. So outcome may be 1, then the output will be 10 sin omega t. Outcome may be 4, then the output will be 40 sin omega t. So output or the signal becomes a chancey. It depends on the chance of the rolling dice. What will be the outcome of the rolling dice, and depends on that the signal will be. Now let's say at t equals to pi by 2, what will be the x? What will be the x? xt. It's very difficult to answer because it depends on the chance what is coming. So the xt could be, so at t equals to pi by 2, xt could be 10, xt could be 20, xt could be 30, xt could be 40, xt could be 60. So the xt depends on the chance of coming out of the experiment, and xt is not fixed. So the output, or rather we can say that the signal amplitude, so the signal amplitude at some point of time, is not deterministic. Rather, it depends on chance. So a random process is not just one signal. One thing you have to emphasize. So a random process is not just one signal, rather it is a family of signal. You should keep in mind. So this should be kept in mind. This should be kept in mind. This should be kept in mind, that it is not a single thing. So that is why it is called a process. So random process is not just one signal. It is a family of signal. Here it is 10 sin omega t, 20 sin omega t, 30 sin omega t, 40 sin omega t, 50 sin omega t, 60 sin omega t. So it's a family of signal. Okay. Let us try to, here so xt is a random signal. So we understand what is the meaning of the random signal, and we understand what is the difference of random signal and the deterministic signal, what we read in btech class 2, btech second year. So now let us try to formalize more. So let us try to formalize the process described above. Let us try to formalize the process described above. How? Suppose we perform an experiment. Suppose we perform an experiment. Suppose we perform an experiment, and outcome of the experiment is zeta. And outcome of the experiment is zeta. So now what could be, we try to draw it. So we have a set which is the outcome of the experiment. So it could be zeta 1. Outcome of the experiment is the set zeta. So that means it could be zeta 1, it could be zeta 2, it could be zeta 3, or it could be zeta n, right? So it could be zeta. So outcome of the experiment is zeta. Now a random variable is a number which assigns the outcome of the experiment. So then a random variable is a number which a random variable is a number let's say is a number x zeta, which a random variable is a number x zeta which assign a number to every outcome of the experiment, of the experiment. So a stochastic process or the random process is the assignment of a function of t and the outcome of the experiment. So a stochastic process is a stochastic process or random process. A stochastic process or random process stochastic process or random process is the assignment of a function of t and zeta. That means a random process is a function. This is important. Random process is a function of time and zeta. So if zeta is zeta 1, then t it will go 1, realization will come. So here we have to emphasize that a random process is as a function of t and the outcome of an experiment. Okay, so it's a function of t and the outcome of an experiment. So x zeta t so is a random process. Stochastic process or random process is the assignment of a function t zeta x t xi to each outcome of an experiment. So then what is random process? Random process is the assignment of a function t. So let's write it. This is important. So random process is the assignment of a function of t to each outcome of an experiment. Okay, so let's try to draw a figure. What I mean to say, it requires a full page. Okay, so let's say we have done one experiment and output of the experiment is zeta 1, zeta 2, zeta 3, like this, zeta n. So with each zeta, we assign a function of time. What does it mean? Let's say a zeta 1. We assign a function. Let's say for zeta 1, we assign a function t. So this is x t zeta 1. Some function we assign. For another zeta, let's say zeta 2, we assign a function t versus xt zeta 2, So this is another function. Sorry, it cannot be double valued. So similarly, we have all the zeta, we assign a function, and for zeta n, we assign another function, which is t versus zeta t comma zeta n which is a function of like this. So this, so with each zeta, each outcome we have a, which each outcome we have a function of t assigned with that. So this individual is called the sample function. So each of these is a sample function. This is a sample function. This is a sample function. Each are sample function, and all the possible zeta when we consider. So we have all the possible signal, which is called the ensemble or family. Family we don't call, somebody may call, but it's an ensemble. Okay. So if we, so what is the difference? A deterministic process is a single function of time, and but a probabilistic process or a random process is the family of function of time. Okay, so that is the main difference. That's why it's called the process. So the set of function. So what is ensemble? So we have, so what we have? We have t zeta 1. We have another experimental outcome t zeta 2. Like that, all the function we have x of t zeta n, right? And the set of all these function, set of all the function corresponding to an outcome of an experiment is called the ensemble. So the set of function, so the set of function constitute of all the, correspond to all the outcome of the experiment zeta n may be capital, we are writing zeta n corresponding to n outcome of an experiment is called an ensemble, and each member t zeta I is called a sample function. Each member is called a sample function of the stochastic process. Sample function of the stochastic process. So how we describe the ith sample function? So we describe the ith sample function. Xt comma zeta I is the ith sample function. So if I want to say that ith sample function, what we'll write? We'll write x of t zeta I. And simple sometimes or many times we write x of I t. Okay. So a stochastic process is collection of all sample functions, right? So we see it earlier. So a stochastic process is a collection of all sample function, collection of all sample function, and is denoted by x t zeta. When we say zeta, that means all zeta are included, or sometimes or many times we call it xt. So when we call the xt, we make the zeta silent, and xt we call, that means zeta is hidden. So the xt is the random process. That means it's a full ensemble. So what is then? So we write it here that the sample set function. So xt comma zeta will be equals to xt will be equals to x1t See, you see here, we call it, it's called the sample function. Yes, see this one. So so it is x1t, x2t, dot 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 xnt, and that is called all the sample function, collection of all the sample function, that is called the random process xt. So zeta is silent here. Okay, now there is an important thing. Suppose we have realized a random process. What does it mean? That means we have a sample function t, which is x1t for some zeta 1, which may be say like this. Okay, and then let's see, we have a t and we have another zeta x2t, and that is maybe like this. And similarly we have all the xt and we have xnt, right? And that could be something like this t, right? Now, so this is, we call this is the sample function, and this is our ensemble. This is our ensemble. This is a sample function and this is our ensemble. So, so let's say we want to see that at time t1, what will be the value of the signal. So let's say this is our time t1. This is time t1. So let's try to draw it. So draw a straight line through the t1. So let's draw it, dotted line. So what is the value over here? Here the value is x1 t1. What is the value over here? Here this is t1. So here the value is x2 t1. Similarly, this is t1, and what is the value over here? Here it is this point. This point is x in t1, right? So what we get? We get the number at particular t1. So at some time t1 we get the number. So those numbers are x1 t1, x2 t1, x3 t1, dot dot xn t1. So if we take the population of that or set of that, how we can write? We can write xt1 will be equals to x1 t1, x2 t1, like this, and we can write xn t1. So this is a set. So this is a set of all the points at the time t1, and this xt1 is important. So if I write anything, let's say xti, that means it means a set of number at particular time, a set of all possible number, which random process at 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 a particular time, ti, a set of number at a particular time ti, a set of number at a particular time ti. So if we see that the random process has the 4 different representation. So what are those? You can see that we can represent it as a sample function, single sample function. We can represent it as a collection of sample function. We can represent it at a number, what at particular time t, what is the number. We can represent it as a collection of all the number at particular time t1. So there are 4 different ways we can represent a random process or stochastic process. So there are 4 different way, a stochastic process or random process can be represented. How they can be represented? 4 different ways. First is what? First is a full ensemble, that the family, an ensemble of time function, an ensemble or family of time function. Full ensemble, an ensemble or family of time function. So it is represented as, so it is represented as x of t comma zeta, or as we say, or simply x of t. You have to see here both t and zeta are variable. Here both t and zeta are variable. Second way how we can represent, there is another way to represent. What is that? For a particular zeta I, when we realize the function, we call it the sample function or realization, then it becomes a function of t, not the function of zeta. So for a particular zeta, for a particular fixed zeta, say equals to zeta I, when we realize the function, when we realize the function for which we call sample function, or which we call sample function, or what we call the realization, which we call the sample function or which we call realization, then t is variable. So for a particular t, then when we realize the function, so then t becomes variable, but zeta becomes fixed. So such realization is called the sample function or the realization, single realization. So when zeta becomes fixed and t is the variable, so this is a kind of, you can say, the time series or single time function. So this is a kind of time series, it's changing with time, or the single time function. Okay, so we represent it as xit. That means I means ith ensemble. Okay, we represent it as xit. This is the second way. What is the third point? So this becomes the sample function. So one is ensemble, this number two is the sample function. What is the third point? Third point is a random variable at some instant. Say t1 is at a random variable at some instant is for some fixed zi is a single number, right? A random variable for a fixed experimental outcome zeta I, and for a fixed time ti, is a single number, just single number, because we fix the zeta, that means the ensemble number or the experimental outcome, and then we fix the time. So what it becomes? It becomes a single number. So we represent it as x I ti. For example, x1 t1 at t1 time, and the first ensemble or at the outcome of zeta 1, what will be the value? It will be the same single value. Okay. Number 4 is another thing left, that is the collection of all these single values. The set of all random variable, at some fixed time ti, or people call it t1 at some fixed time t1, set of all random variable at some fixed time t1 over the ensemble, over the ensemble. That means you see how we can represent it. You see how we can represent it. So one way we can represent it as a single, this way. This is a one way of representation, right? And the all the things we can represent, all the things we can represent as well. So all the things we can represent, this is another way of representation. This single thing we can represent, single function of t, that is one way of representation. This number x of t1, this is the another way of representation. And the collection of all these things over ensemble, this is also, this also we can say this is the collection of this. So this is the, so there are four ways we could represent. One is the full ensemble, that means xt, right? And another is the sample realization, that means say xit. Another is the single point, that means say xiti or say t1. And then another is the all the collection of all these single points, that is over ensemble, that is xt1. So there are four ways we could represent a random process. So four ways we could say we could represent a random process, four different way. Okay, so that means xt, when you say this is a collection of all sample function over the ensemble, that is the total representation. xit is a single sample realization, single sample function, a single realization. Collection of xit will be the xt. And then a single number realization, when a single ensemble and a single sample function at some particular time, this is xit1. And then collection of all xit1, that means that particular time the random variable collection over the ensemble is xt1. That is the another way of representation. So there are total four ways of representation. So this I must say, I must complete it. So number 4 is set of random variable when at some fixed time ti or t1 over the ensemble, over the ensemble. So here the time is fixed, here the time is fixed, and the ensemble and the population is generated over the ensemble, and the population is generated over the ensemble. So we represent it as, so we represent it as, how we represent it? We represent it as x of t1 or ti. If we represent it, we say it is x of ti or t1, sometimes called x of t1. So the statistics of over random variable over the ensemble can also be calculated, and it is a very important, it plays a very important role in random process, in realizing random process and in analyzing a random process. The statistics of random variable over the ensemble, the statistics of random variable over the ensemble can also be calculated. Okay, that means let's say x of t1, what will be the mean? We can calculate it, can be calculated, and statistics play a crucial role in understanding and realizing or understanding or realizing or characterizing a random process. So let's end here today. Next day what we'll do that the different classes of stochastic process: discrete, continuous time, discrete time, continuous amplitude, discrete amplitude. How many ways we can classify a stochastic process, that we'll discuss in the next class. Okay, so bye everybody.